So yeah, I'll be continuing talking about this. I'll repeat a lot of the motivation that Madhur said, but I'll try to be a little faster about it. Uh, so just the obligatory error correcting code slide. A code is just a subset of sigma to the n for some finite alphabet. We think of it as encoding some message, which is a k-length string into n-length string. And these are supposed to be encoded in a way that even if a code word is passed through a noisy channel, you can recover what the intended code word was. And typically this is ensured by saying that the encoded messages, the code words will have some sort of distance property, so that even if some positions get corrupted, you can recover the original intended message. The code C will be linear if it's not just a subset, it's a subspace. And the distance we'll be talking about in terms of normalized Hamming distances, so between 0 and 1. And the rate is going to be this fraction k over n, again, between 0 and 1. So this is going to be my code. If all the points here are well separated, then if the corruption is less than delta over 2, where delta is the threshold of separation, then I can at least theoretically hope to get back to y from y tilde. Okay. And the most basic bound in coding theory is the trade-off between this distance and rate, which have a natural tension between them. And the singleton bound says that the sum of these two parameters cannot be more than 1. You would want them to be as close to 1 as possible. You want them to be as high as possible, but both can't be high simultaneously. So if we fix a rate r, the best distance we can hope for is 1 minus r. Okay, and correspondingly, if we are doing unique decoding, we are only doing it up to half the distance, which means that the unique decoding radius cannot be more than 1 minus r over 2. And the great thing is that we do have these Reed-Solomon codes which achieve the singleton bound. These are based on bounded degree polynomials over some finite field. The message can be seen as all the coefficients that we would have for the monomials. And the code word is just evaluations of these polynomials on n distinct points. The rate is just going to be the number of coefficients we have, the number of monomials, divided by number of evaluation points. So we can choose those parameters so that the rate is r. And any two degree k minus 1 polynomials, degree k polynomials can agree in at most k positions. And this directly implies distance. They achieve the singleton bound. They are encodable in near linear time, decodable from half the distance. They're used all over the place, from practical applications to theoretical ones like constructing good binary codes. They were instrumental in constructing the first explicit family of good binary codes. And of course, they have a lot of applications to theoretical CS as well. And in many ways, like, they are the king of codes. But there are some drawbacks. And one of the drawbacks is this encoding time or decoding time has been stuck at near linear for a long time. But there are other codes that support truly linear time encoding and decoding. And similarly, alphabet size has to be at least n for Reed-Solomon code, simply because we need n distinct points in the field to evaluate the polynomial on. And these codes are not very flexible in the sense that if I have my own favorite code with a certain property, I don't know how to get the best of both worlds like this. And the AEL construction should be seen as a challenger in some sense, where you get similar rate distance trade-offs up to this epsilon. But you can start from any base code. All we need this base code to be is a high rate code. So when the rate is high, say 1 minus epsilon, the distance has to be small, right? That's just singleton bound. What we are saying is that rate can be lowered and distance can be boosted in a near optimal way. So distance goes from very small to 1 minus r, and the rate falls from 1 minus epsilon to r. You can do this while keeping the alphabet to be constant and not dependent on n. Okay. These were originally introduced by Alan Edmonds and Luby to correct 1 minus r minus epsilon erasures in linear time. When we are talking about erasures, these are just errors where you know the location. So the received word could look like a bunch of question marks on those positions. For a linear code, it's not difficult to correct erasures in polynomial time. You can just use Gaussian elimination, but the question is, can you do it in linear time? And these were the codes to do it for the first time in this optimal distance kind of regime. They, like using base codes that are very efficiently encodable and decodable, we can get optimal rate distance trade-offs along with those linear time encoding and decoding time complexity. And the alphabet size depends on epsilon, but not on block length. Then it's a flexible construction. It can be made LDPC. It can be made locally testable if you choose the starting code to be, and so on. Let's go into a bit of what these AEL codes are. These are based on, like Madhu described, biregular spectral expanders. So we'll just say that the biadjacency matrix of the bipartite graph, if it has a small normalized second singular value. The most obvious example of such an expander would be the complete bipartite graph, but it's not super useful because you want sparsity in these graphs. You can take the double cover of a Ramanujan graph, which are fairly explicit expanders, and get a lambda, which is roughly 2 over square root d. So if I want a constant small lambda, I need to have somewhat large d, but it can be independent of n, unlike the complete bipartite graph. And the whole point of having this lambda expander is to get this sort of mixing properties. In fact, we'll just need one-sided expander mixing lemmas, which is to say that the number of edges between any s on the left, t on the right, is upper bounded by the global edge density, which is d over n, times the number of slots between them. The number of slots is s times t. The global density is d over n. If these were truly random, we would just get d over n times s times t. Up to some error dependent on lambda, this is what happens. Okay. The AEL amplification, again, Madhu described a lot of this, but just to reiterate, you start with this base code, which can be seen as an outer code in a concatenation scheme where you encode your message into a big message and then big message over a large alphabet, and then each alphabet symbol of the coordinate is encoded by a further inner code, by the same further inner code. And if you just did concatenation, the parameters of the two codes just multiply. Which means, like if, let's say the inner code was binary, I would get finally a binary code. I would want it to be as close to RC in and delta n as possible. Then I would get something that was a constant size object, but a global family. And maybe I want rate to be very close. I could choose RC out to be very close to 1, but then the delta would have to be very close to 0. So I have to lose in one of the two. But then AEL amplification says that you do some post-processing on that based on an expander, and you can do much better in terms of distance. So for, like, after you fold these edges that we got from a concatenated code along the other side of the expander, the distance goes from just the product of delta in and delta out to something that is decoupled between delta in and delta out. So it becomes delta in minus lambda over delta out. And now I can choose, even if delta out was small, I will choose lambda to be even smaller and get something close to delta in. Right? So typically the way this is done is you choose RC out to be very close to 1, delta out then is forced to be close to 0, but then you choose lambda to be even smaller. Okay. And on the right-hand side, what is going on is you are folding symbols and calling them a single new symbol. And why this works is basically if you have two code words that are somewhat distinct on the left, let's say they are distinct in these two positions, then their corresponding encodings on the edges will be different. But because it is an expander, the other side will be somewhat pseudo-random, and these edges will go spread out all over the place. That's roughly the idea. So even if they differed only in these two positions here, they might differ in a lot of positions here, because all I need for the two encodings to be different is for one of the edges to be different here. So we're comparing Reed-Solomon and these expander-based constructions. One field in which they definitely lag behind is list decoding, where we want to correct more than delta over 2 errors. Recall that for delta over 2 errors, AEL codes can be decoded in linear time. And beyond delta over 2, first of all, we need to have at least 2 code words in the list now. But maybe the hope is that the number of code words is polynomial, if not 1. Then at least we can hope for a polynomial time algorithm. If the list is exponential size, then it's kind of hopeless. The hope does come true. There is always a threshold between delta over 2 and delta, up to which the list is bounded. And this is the Johnson bound. When this delta is of the form 1 minus r, the Johnson bound is 1 minus square root r. And the algorithmic task is to find the list. The combinatorial bound just holds based on the distance for any code. But the algorithmic task is often not clear. So if we have this sort of received word f tilde, then up to delta over 2, then we can draw these two balls of radius, delta over 2 and the Johnson radius. Up to delta over 2, we know that there will be only one code word. Beyond delta over 2 up to j of delta, there might be more code words, but there won't be too many of them. Maybe there are 4 more, but that's it. Okay. So for algebraic codes, seminal works of Guruswami and Sudan showed that you can efficiently decode them up to the Johnson radius. And later breakthroughs actually made it optimal. 1 minus r is the best we can do. And some variants of Reed-Solomon codes that you obtain just by folding symbols together, they can be decoded up to the optimal radius. Recently, Chen and Zhang showed that the list size also can be made optimal for those very codes without any modifications. So just to summarize, these algebraic codes have optimal radius, optimal list size, and near linear time. What Madhu's talk showed was that AEL also has optimal radius and optimal list size. What about time? So in terms of time, there are polynomial time algorithms that are based on sum of squares programs, but they're really just polynomial time algorithms. So the exponent of n is a huge constant, independent of n, but depends on epsilon in a very bad way. And in particular, they are nowhere close to quadratic or cubic, definitely not linear, etc. So can we remedy this situation? And it's even more important because for expander-based codes, the unique decoders are linear time. And these AEL codes, now that we know that they can be decoded with optimal list size up to optimal radius, maybe there is a linear time algorithm waiting to be discovered there, which would give a truly linear time code decodable up to the optimal radius, which we probably do not expect Reed-Solomon to do, because there even the unique decoders don't run in linear time. So our main result is a near linear time algorithm to decode this construction. So this is roughly what Madhur's talked about, that you can adapt AEL construction so that it's list decodable up to 1 minus r minus epsilon with list size order 1 over epsilon. And the new contribution is that there's also a decoding algorithm that runs in time near linear. Okay. And as is the case with a lot of decoding algorithms for AEL, it's actually a reduction for decoding the AEL code to decoding the base code. Just like it's an amplification for the distance proof, all the decoding algorithms turn out to be reductions for decoding the AEL to decoding base code. But the base code can be, base code decoding can be for arbitrarily constant, small constant fraction of errors. The near linear time algorithm is randomized, can also be made deterministic, but then it won't be near linear time. But at the same time, it's not going to be crazy. Probably n cube, n to the 4 kind of dependence. And with all of these modifications, it's good to remember that unique decoding is still linear time. It's the same code that we are using. It's just that we are augmenting more properties on top of it. It still has all those nice properties that we talked about before. So let's see how unique decoding AEL goes and why it is linear time. So this is our graph. Let's say G is some, I'll try to use G as the received word mostly and H as the true list code word. Let's say G is the received word that we'll have on the right-hand side. G is going to be actually R symbol. So R is the set of right vertices. G is going to be sigma into the D symbols. Sigma in is the alphabet of the inner code here. So it's going to be D symbols, one for each vertex. You can always unfold it and talk about sigma in symbols on all the edges. That's just a way of packaging. And the property that we are given is that G has some true code word H that lies close to it, that lies under distance 1 minus R over 2. How do we decode this? Well, based on G on the right-hand side, we can look at all the local received words it induces, because G is really a labeling of the edges. And the natural thing then to try is to just decode these local ones. We could try decoding this G1, G2, G3, and so on. If it turned out that, let's say H is the true hidden code word, if HL is the unique thing close to G2 here, then we are good. But it might not always happen. What can be shown is that when we decode these G1 through Gn, we'll get a lot of these H1 tilde, H2 tilde, and so on. What can be shown is that if the global distance between G and H is small, then simply by another application of expander mixing lemma, mostly GL and HL will also be not too far for most vertices. This is again some sort of sampler property or expander mixing lemma. If they are too far, if GL and HL are too far on a lot of vertices, then G and H cannot be so close on the right. That's pretty much it. And if GL and HL are super close, that also means that these HL tildes are actually HL, right? Because the unique decoding is just going to find that correct HL. These are constant size objects, so we can afford to do whatever brute force search for decoding that we want. And then the outer code can fix whatever remains, whatever bad vertices remain. The number of bad vertices can be controlled very easily just by boosting expansion. Okay. What breaks down when we try to go beyond delta over 2? Why don't we have a clear cut? By the way, this algorithm that I just talked about is linear time if the base decoder was linear time. It's also deterministic, parallel and everything. It's really clean. Okay. So what breaks when you go beyond delta over 2? You could try still the same strategy. You take this G, you get a bunch of these induced G1 through Gn. You can again try to decode. But now that we are decoding beyond delta over 2, we'll start getting lists here. The sampler property is still going to tell you that any true code word is going to be represented in these lists. But which one is it? We don't know. And let's just take the easy case when the lists are of size 2. This becomes a problem already at that point. So now we have two candidates for each vertex. We don't know whether F31 went with F42 or F31 went with F41 in the final thing. And this is really the bottleneck. We don't know how to deal with this. Prior applications tried to use a very strong list decoding property for the outer code already. You can get some useful things out of it. But the kind of applications we want, we are dealing with just a unique decodable outer code. So what can we say there? And all of this question is to say, how do we stitch these lists together in a consistent way? Okay. So our main insight is that regularity lemmas can help do the stitching. And we'll talk more about regularity lemmas, but it should be clear what the problem, at least here, is compared to unique decoding. Let's take a detour into regularity lemmas. So let's say we have a complete bipartite graph with all n square edges. And the vertices are left set is called L, right set is called R. Let's fix some set of vertices B on the right. Then if I want to count the number of edges between A and B, let's trivially true that it only depends on the size of A. It doesn't matter which A I'm talking about. Okay, because we have all the edges here. This is certainly not true if you don't have a complete bipartite graph, because some part of left set might have a lot of edges to B, some part might not have a lot of edges to B. Right? Regularity lemmas are these really nice statements that will tell you that if you're willing to live with some eta times n square error, and let's say my graph had a lot of edges so that this eta times n square is insignificant, then this edge count is only going to depend on the density of A, now not globally, but over some partition. So there will be some fixed partition, and it's important the order here. The partition is fixed first, and then it works for all B. So there is a fixed partition of L such that whenever I want to look at this edge count, then it only depends on what is the fraction of vertices of A in a particular part of the partition. Okay. And if we are willing to live with eta n square error, the partition P has number of parts that only depend on eta. Of course, you can always do this with the partition being all vertices. That's the trivial thing. The good thing here is that the partition is only constantly complex in a way. Okay. But this eta n square error is just useful for dense graphs, not for sparse graphs. There is a regularity lemma also for sparse graphs. And recall, first, our model was actually complete bipartite graph. In the sparse case, that model is going to be the expander, where again, it is true that if you have any set B, the edge count is only going to depend on the size of A. That's expander mixing lemma. And now the regularity lemma is going to be for subgraphs of expanders. Just like previously, it was for dense graphs. Now it is going to be for all subgraphs of expanders. And we can change the eta n square error to eta nd error, nd being the number of edges in the expander. Okay. What you do need is lambda to be sufficiently small, the expander to be sufficiently good in terms of this eta. But if you are given the flexibility to make lambda as small as you want, you can always do this. So there is a partition such that for every B, the edge count, e.g. A comma B, only depends on densities of A under P. So actually, the regularity lemma is going to give you, there's a partition P of L, there's a partition Q of R, such that the edge count only depends on the densities of A under L, A under P, and B under Q. But we don't really need the other side. But the regularity lemma will give you both partitions. Okay. Is that a how much time do I have? 5 minutes. So this is the regularity lemma. How do we prove this? Well, you just start with the trivial partition, which has everything, and you iteratively refine it until you get to that property. And it can be shown that this process only lasts some constantly many times, depending on eta. This is a standard way of proving weak regularity results, or really all regularity lemmas. How do we do this algorithmically? Well, you use this refining part coming from the output of some cut norm approximation algorithm. Yes, so this algorithm, the cut norm approximation, can be made to learn in near linear time. And really, this is the only non-linear time step in our algorithm, because this can only be done in near linear time and not truly linear. Once you have the regularity partition, everything else is linear. Okay, but what I talked about for regularity lemmas, etc., is actually, I'm talking more about sets, etc. How do I bring back the code words? So this was the picture, remember. We have a lot of these local lists that are of size 2. And the question is, how do I stitch them together in a consistent global way? First of all, I can always assume that each list is on the left is actually of size exactly 2. I can always pad it with extra code words. If the decoding here has an upper bound of size 2, this can be extended to bigger upper bounds. And let's say this list of 2 elements is going to be ordered. So there's a first element, there's a second element. And I choose this arbitrarily beforehand. Now the picture looks like this, that I have for every vertex 2 code words here. And the true global code word H is hiding either as the second guy or the first guy or the second guy or the first guy. Maybe in a very small fraction, it's just not present at all. But mostly it's present as either the first guy or the second guy. Let's say we fix such a global code word H. We define disjoint subsets A1 and A2 of L based on whether it's the first thing in the local list or the second thing. And really finding H reduces to finding these A1 and A2. That's not too difficult to see. How do we find these A1 and A2? Well, we construct 2 subgraphs of the entire expander G, such that for H1, you delete all edges of G, where if I were to choose all the first assignments here, some things might become inconsistent with G from the other side. So for every edge G, if the first guy here and the vote from the other side by G, these do not match up, I delete that edge. So it's going to be a subgraph of an expander. Similarly, I construct H2 based on the second code word here. And let's say we have the P1 and P2 are the 2 regularity partitions we get for based on this subgraph of expander. The key claim is that A1 and A2 are actually going to have densities close to 0 or 1 on all parts of P. So we construct these 2 graphs, H1 and H2, that clearly can be constructed algorithmically. You find these P1 and P2, maybe take their common refinement, and then A1 and A2 are just going to look like either all 0, like they have entire part, or they don't. It's not going to be roughly balanced. It's never going to be roughly balanced. So this is some sort of combinatorial rigidity property that we show. I'm going to skip talking about this and just focus on the final algorithm that we get out of this. You get an input receipt word, construct these local lists, construct the 2 graphs H1 and H2 by deleting edges if there is inconsistency. Take partitions P1, P2 of the subgraphs of expander, take their common refinement, and then just brute force enumeration over everything in the partitions that we see. What we'll get is something very close to A1 and A2. And then the base code unique decoder will do the rest of the job. Okay. We actually get some other very interesting things. So first of all, this, if you notice, I also get some sort of combinatorial proof on the list size here. And I did not use anything that Madhu talked about. So this is actually a new, different combinatorial proof that AEL also achieves list decoding capacity. it has better alphabet size to Venkat's question that it's only 2 to the poly 1 over epsilon. But the list size is not perfect like 1 over epsilon. The list size is going to be worse. And it extends to list recovery, which is not tackled in the other line of work. And these are just simple extensions using these regularity lemmas. You can get explicit LDPC codes that achieve list recovery capacity. And finally, for Tanner codes that are defined using bipartite spectral graphs where the code words are all assignments to edges with local checks, these methods will give new list decoding algorithms that go beyond the Johnson bound. And in fact, they'll give new results, both combinatorial and algorithmic, again in near linear time. And they match the dense analog of Tanner codes, which are tensor product codes. So there's this result of Gopalan, Guruswami, and Raghavendra that says that up to a certain threshold, tensor codes can be decoded. You can get the same radius for the sparse versions of Tanner codes. To finish up, the most important question here is, can we get rid of this near linear part and truly get linear time decodable codes? For unique decoding, we know how to do that. For list decoding, it's not clear. Sparse regularity lemmas are basically being used here to stitch together these partial local assignments into globally consistent ones. And this is really the key way in which list recoverable codes are used beyond codes. So there are applications to hitting sets, etc. Can we go back to those applications and directly try to use expanders instead of using a black box list recoverable code? And these local to global, here the kind of proof that we did was actually just using list size bound instead of the sum of distances version that Madhur talked about. And these things are more flexible in some settings. So for example, for quantum codes, we don't know about these generalized singleton bounds, etc. But maybe you can always talk about some cardinality bound on the list. Can you use that to get better codes? And of course, binary codes. Again, something where if you just have list size bound, can you get something for expander based codes? That's all.
Questions for Shashank?
Yes, only in the regularity lemma step. And in fact, even there, only solving cut norm, which is an STP. You need to do that very fast, so you need to do some random projections. That's pretty much it. Right. Running time of the algorithm, yes. Alphabet size, no. Alphabet size, you get a 2 to the poly 1 over epsilon kind of bound.
The list size bound is also this doubly exponential,
Yes,
and the random
yes,
time.
yes. Some of that might be fixable, but definitely exponential. Yeah, no, that's in fact true. Right, right. So you do get a true list size of 1 over epsilon because you do know that from the other proof. So yeah, you get new combinatorial results, but if you use it in the setting where you do know better results, and that is how you should use it, then you'll get the optimal list size as well.